This is a young planetary system still forming within a cloud of dust and gas, orbiting a newly ignited star. Countless fragments of rock and metal collide, merge, and shatter in chaotic orbits. Among them is a growing rocky world, hot, unstable, and constantly bombarded. Its surface is molten in places, its interior churning, its future uncertain. Around it, debris moves at tremendous speeds, remnants of planetary construction still clearing their paths. Gravity is shaping everything, pulling matter inward, forcing collisions that will decide which bodies survive and which are erased. One object, roughly the size of a small planet, follows an unstable orbit. Its path crosses dangerously close to the larger rocky world. Over time, gravitational interactions alter its trajectory. Each pass pulls it closer, stretching its orbit, increasing the likelihood of impact. There is no intention, no warning, only physics at work. Velocities increase, distances shrink. The moment approaches when the collision occurs. It is not a single instant, but a process lasting hours. The impact happens at tens of thousands of kilometers per hour. The smaller planetary body strikes at an angle, not directly head-on. The energy released is beyond comprehension. Rock behaves like liquid. Metal vaporizes. Shock waves travel through the larger planet's mantle, reshaping its interior. A massive portion of the outer layers is blasted into space, forming an expanding disk of superheated debris. Temperatures reach thousands of degrees. The surface of the planet becomes a global ocean of magma. The atmosphere, if one can call it that, is stripped away and replaced by vaporized rock and metal. The impacting body does not remain intact. It is torn apart instantly, its material mixing with that of the larger planet. For a time, there is no solid ground, no sky, only incandescent chaos orbiting a glowing sphere. As the debris spreads outward, gravity begins to act. Fragments collide again, clumping together within the orbiting disk. Larger pieces sweep up smaller ones. Over days, then months, then years, the material organizes itself. The planet below begins to cool, its molten surface slowly losing heat to space. Above it, the orbiting debris continues its silent assembly. From this disk, a single, dominant body begins to emerge. At first, it is irregular, a loose collection of molten fragments. Impacts continue, smoothing its shape, pulling it toward a spherical form. Its orbit stabilizes. Over thousands of years, it becomes a companion, bound by gravity, to the planet below. A satellite is born. The formation of this satellite changes everything. Its mass exerts a constant pull on the planet. The planet itself is no longer spinning as it once did. The angled impact has altered its rotation. Instead of spinning upright relative to its orbit around the star, it now tilts. This tilt is not extreme, but it is permanent. It will define cycles of light and darkness, warmth and cold, over vast stretches of time. The planet's rotation also slows. Angular momentum has been transferred to the newly formed satellite. Days become longer. The surface, still cooling, begins to stabilize. The molten oceans gradually solidify into a crust, though volcanic activity remains intense. Cracks form, plates begin to shift. Heat escapes from the interior through fissures and eruptions. Above, the satellite continues to evolve. Initially, much closer than it will be in the future, it dominates the sky. It appears enormous, glowing from retained heat. Its gravitational pull interacts strongly with the planet. Tidal forces flex the planet's crust, generating additional heat. These forces also stir the molten interior, preventing it from cooling too quickly. Tides begin to shape the planet long before liquid water exists. The crust rises and falls rhythmically under gravitational stress. This motion helps redistribute heat and materials within the planet. Over millions of years, the satellite slowly moves farther away, but its influence remains profound. The planet's tilt, established by the collision, introduces variation. Regions receive different amounts of stellar energy over time. Without this tilt, the planet's climate would be far more uniform. With it, patterns begin to form that will one day allow complexity to arise. The collision, though violent, has set the conditions for long-term stability. The satellite also acts as a stabilizing force. Without it, the planet's axial orientation could vary wildly due to gravitational interactions with other bodies in the system. Instead, the tilt remains within a relatively narrow range. This stability persists for billions of years, preventing extreme climatic shifts that could sterilize the surface. In the immediate aftermath, however, the planet remains hostile. The surface is a glowing landscape of lava, seas, and erupting volcanoes. The atmosphere is thick with vaporized rock, carbon compounds, and other gases released from the interior. There is no solid land for long. Impacts from leftover debris continue, adding energy and delaying cooling. Gradually, over tens of millions of years, the bombardment decreases. The star's radiation and the vacuum of space draw heat away. The magma oceans begin to freeze. A solid crust thickens, though it is constantly recycled by tectonic activity. Gases trapped within the planet escape through volcanic vents, building a new atmosphere. This atmosphere is dense and opaque. Light from the star struggles to reach the surface. Heat is trapped efficiently, keeping temperatures high. Yet this same atmosphere prevents rapid heat loss, allowing the planet to cool slowly rather than catastrophically. Balance begins to emerge. The satellite's orbit continues to influence the planet's rotation. Each tidal interaction transfers a small amount of energy. Days lengthen incrementally. The planet's internal dynamo, driven by heat and motion within its core, generates a magnetic field. This field shields the surface from charged particles streaming from the star, protecting the atmosphere from being stripped away. Without the collision, without the satellite, this magnetic protection might never have developed as it did. The impact reshaped the core, enhancing, mixing, and sustaining the dynamo for billions of years. Invisible lines of force now surround the planet, deflecting harmful radiation and preserving the gases necessary for future transformation. Above the surface, the satellite settles into a more circular orbit. Its surface cools faster than the planet's, lacking a thick atmosphere or strong internal heat sources. Craters form and remain, recording the history of impacts that no longer reach the planet with the same frequency. The satellite becomes a silent witness, orbiting faithfully. The planet, meanwhile, is entering a new phase. Though still inhospitable, it is no longer entirely molten. Solid ground exists, if only temporarily. The crust breaks and reforms. Heat continues to escape, but at a manageable rate. The atmosphere thickens, enriched by gases released from deep within. Clouds of mineral vapor swirl overhead. Lightning flashes through dense skies. Chemical reactions occur constantly, driven by heat, pressure, and energy from the star. The surface is reshaped again and again, erasing and rewriting itself. The tilt causes uneven heating. Some regions cool faster than others. Differences in temperature drive powerful winds. The atmosphere circulates, distributing heat around the globe. This circulation, though primitive, prevents extreme conditions from dominating permanently. The satellite's gravitational pull creates tides, even in the molten mantle. These tides contribute to ongoing geological activity, keeping the planet alive internally. This internal motion prevents stagnation, ensuring that materials from deep within can reach the surface and interact with the atmosphere. Over immense spans of time, the violence of formation gives way to slow evolution. The planet is no longer just a product of random collisions. It is becoming a system, with interconnected processes influencing one another. The collision that formed the satellite has imposed order on chaos. The satellite reflects light from the star, illuminating the planet's night side. Though faint compared to the star, this reflected light adds energy, however small, to the surface. Nights are not entirely dark. Rhythms of illumination begin to emerge, even before life exists to perceive them. As millions of years pass, The planet continues to cool. Volcanic activity remains widespread, but gradually becomes less uniform. Certain regions become more stable. Crust thickens. The atmosphere changes composition as lighter gases escape to space and heavier ones accumulate. The satellite continues its slow retreat, moving centimeters farther away each year. This gradual change subtly alters tidal forces, lengthening days further. The planet's rotation becomes more measured, less frantic than in its earliest state. The impact that created this configuration was not unique in the system. Other worlds experienced collisions as well, but the outcome here was balanced. The angle, speed, and mass involved produced neither total destruction nor insignificant change. It was a narrow outcome among countless possibilities. The planet now exists with a companion that will shape its destiny. The tilt ensures variation. The tides ensure motion. The stabilized rotation ensures predictability. None of this was guaranteed. Each aspect is a consequence of that ancient collision. In space, time stretches. What seems catastrophic on short scales becomes foundational over longer ones. The debris that once glowed white-hot has assembled into a permanent feature of the sky. The molten surface has begun its slow transition towards solidity. The atmosphere, though harsh, is a necessary precursor to what will follow. The system is not finished forming. Smaller impacts still occur. Energy still flows, but the most violent chapter has passed. The planet and its satellite are now locked in a gravitational relationship that will endure for billions of years. This moment marks a turning point. From chaos, structure has emerged. From destruction, stability has been forged. The planet is no longer merely surviving its formation. It is preparing, unknowingly, for transformations still far beyond the horizon. Processes that will depend entirely on the conditions set in motion here. As heat dissipates, orbits stabilize, and the long aftermath of the collision continues to unfold without pause. The planet continues its slow transition from a molten world toward one with a solid surface, but the change is uneven and unpredictable. Vast regions remain unstable, periodically remelted by internal heat and resurfaced by eruptions. Lava flows spread across thousands of kilometers, cooling into dark, jagged plains before being broken apart again by tectonic stress. The crust is thin and fragile, constantly fractured by the movement beneath it. Nothing remains fixed for long. Above the surface, the atmosphere grows denser. Gases released from the interior accumulate layer by layer. Carbon compounds, nitrogen, sulfur-bearing molecules, and water vapor dominate the sky. Pressure at the surface increases dramatically. The air is thick, hot, and opaque, scattering light and trapping heat. The planet glows faintly even at night, radiating stored energy back into space. The satellite remains close enough to loom large overhead. Its gravitational pull continues to knead the planet's interior, stretching and compressing rock with every orbit. These tidal forces generate additional heat, particularly along fault lines where the crust is weakest. Volcanoes erupt in chains, releasing plumes of gas and ash that rise high into the atmosphere before collapsing back onto the surface. As the planet cools, heavier elements sink toward the core, while lighter materials rise. This differentiation strengthens the internal structure. The core remains molten and dynamic, driving convection currents that sustain the magnetic field. Invisible but powerful, this field deflects charged particles from the star, reducing atmospheric loss and preserving the volatile compounds accumulating near the surface. The tilt, imposed by the ancient collision, continues to influence energy distribution. One hemisphere leans toward the star for part of the orbit, receiving more heat, while the opposite hemisphere experiences relative cooling. These differences intensify atmospheric circulation. Massive storm systems form, driven by temperature gradients, far more extreme than anything that will exist later. Lightning becomes common. Electrical discharges crack through the dense clouds, releasing bursts of energy that trigger chemical reactions. Molecules collide, break apart, and recombine into new forms. The atmosphere becomes a chemical laboratory, its composition slowly evolving through countless reactions powered by heat, radiation, and electricity. The surface bears the scars of constant change. Impact craters from remaining debris puncture the crust, though many are quickly erased by geological activity. The rate of impacts declines steadily as the system clears itself of leftover fragments. Each passing million years brings fewer collisions, allowing the surface to persist longer before being reshaped. The satellite's orbit continues to widen, but only gradually. Its presence stabilizes the planet's rotation, preventing chaotic wobbling. Without this stabilizing influence, gravitational interactions with other bodies could cause dramatic shifts in orientation. Instead, the tilt remains relatively steady, preserving long-term patterns of illumination and temperature. Over tens of millions of years, the planet's surface begins to show the first signs of enduring structure. Large regions of crust thicken enough to resist immediate recycling. Primitive continental masses begin to form, not yet permanent, but more resilient than the transient surfaces of earlier epochs. These regions float atop the mantle, moving slowly, colliding, separating, and reforming. The atmosphere begins to stratify. Lighter gases rise to higher altitudes, while heavier ones concentrate near the surface. The pressure becomes sufficient to support condensation under the right conditions. Water vapor, abundant in the atmosphere, exists in a superheated state, unable yet to form liquid due to extreme temperatures. Heat continues to escape, however, inexorably. The star's energy input remains relatively constant, but internal heat slowly diminishes. Over time, the balance shifts. Average surface temperatures begin a long, gradual decline. The planet is still hostile, but it is changing direction. Cloud layers thicken and persist. Some reflect stellar radiation back into space, cooling the surface slightly. Others trap heat, maintaining high temperatures below. The interplay between these effects creates fluctuations, periods of relative cooling, followed by renewed warming driven by volcanic outgassing. The satellite's gravitational influence produces tides not only in the solid crust but also in the atmosphere itself. Air masses rise and fall subtly in rhythm with orbital cycles. These movements contribute to mixing, preventing stagnation, and distributing heat and chemicals globally. As millions of years pass, the planet's rotation slows further. Days lengthen from hours to tens of hours. This slower rotation alters atmospheric dynamics. Storm systems grow larger and more persistent, spanning significant portions of the globe. Wind patterns become more organized, following predictable paths shaped by rotation and tilt. The surface cools enough in some regions for solid rock to persist for extended periods. Dark basaltic plains stretch across vast areas, interrupted by towering volcanic constructs. These volcanoes release enormous quantities of gas, replenishing the atmosphere and counteracting cooling trends. Each eruption is both destructive and essential, part of the planet's ongoing self-regulation. The magnetic field remains strong, shielding the upper atmosphere from erosion. Charged particles from the star are diverted around the planet, producing auroral phenomena high above the surface, though unseen by any observer. These interactions mark the planet's growing resilience. Chemical reactions continue relentlessly. Simple molecules form more complex ones through repeated cycles of breakdown and recombination. Some compounds settle onto the surface, only to be vaporized again by heat. Others remain suspended in the atmosphere, participating in further reactions. The planet's chemistry grows increasingly diverse. The satellite, cooling more rapidly, develops a solid crust marked by extensive fracturing. Its surface becomes a record of ancient impacts, preserved due to the absence of significant geological recycling. From the planet below, it appears as a constant presence, its phases cycling predictably as it orbits. Gravitational interactions between the planet and satellite gradually synchronize certain aspects of their motion. The satellite begins to show the same face toward the planet consistently. Tidal locking establishes a permanent orientation, fixing surface features in relation to the planet below. The planet's oceans do not yet exist. but conditions are slowly approaching a threshold. As temperatures decline, water vapor approaches its condensation point during cooler periods. For now, any liquid that briefly forms quickly evaporates or is boiled away by residual heat. The crust thickens further. Tectonic plates become more defined, their boundaries marked by intense activity. Subduction zones recycle surface material into the mantle, while spreading centers create new crust. This constant motion prevents the buildup of excessive heat beneath the surface and allows chemical exchange between interior and exterior. Atmospheric pressure reaches levels far higher than those experienced later. The weight of the air compresses the surface, influencing chemical reactions and physical processes. Gases dissolve into molten rock and are later released, altering atmospheric composition over time. The tilt continues to impose seasonal variation. Those seasons are extreme compared to the future. Temperature differences between hemispheres drive powerful circulation patterns. Heat is transported from warmer regions to cooler ones, moderating extremes and preventing runaway cooling or heating. Over hundreds of millions of years, the planet transitions from a world dominated by internal heat to one increasingly influenced by external energy from its star. This shift marks a fundamental change. The surface environment becomes more stable, though still volatile by later standards. The satellite's retreat slows slightly as tidal interactions weaken with distance. Its influence remains significant, but less intense than in the earliest epochs. The planet's rotation stabilizes further, approaching a rhythm that will persist for billions of years. Volcanic activity, while still widespread, becomes more localized. Certain regions emerge as persistent hotspots, while others cool and remain relatively inactive. These stable regions allow the accumulation of thicker crust and the formation of long-lived landmasses. The atmosphere begins to clear marginally. As volcanic outgassing fluctuates, periods of lower gas release allow clouds to thin, permitting more stellar radiation to reach the surface. This additional energy can temporarily reverse cooling trends, demonstrating the delicate balance governing the planet's climate. Chemical sediments accumulate in low-lying regions, formed from atmospheric compounds settling out of the air. These materials are repeatedly reworked by heat and tectonics, but their presence marks increasing chemical complexity at the surface. The magnetic field continues its protective role. Without it, lighter atmospheric components would be stripped away over time, leaving the planet dry and barren. Instead, the atmosphere remains thick, retaining water vapor and other volatiles essential for future developments. The planet's interior slowly loses heat, but not uniformly. Convection persists, driving plate motion and sustaining the magnetic field. This internal activity ensures long-term geological vitality, preventing the planet from becoming geologically dead too early. The satellite's gravitational pull still raises tides in the planet's crust, but the amplitude decreases as distance increases. These tides nonetheless continue to contribute to internal heating and mixing, albeit at reduced levels. Over immense timescales, the combined effects of cooling, atmospheric evolution, and geological activity bring the planet closer to a critical transition. Conditions are approaching a point where liquid can persist on the surface, at least intermittently. Clouds grow heavier. During cooler intervals, droplets form within them, only to evaporate before reaching the surface. These brief episodes hint at a coming change. The atmosphere is on the verge of supporting sustained condensation. The surface temperature continues its slow decline. Lava oceans shrink, retreating to isolated regions. Solid ground dominates more of the globe, though it remains scarred by volcanism and tectonic upheaval. The planet is no longer defined solely by its violent birth. It has entered a prolonged phase of preparation, shaped by the consequences of that ancient collision. The satellite remains in orbit, the tilt remains fixed, the magnetic field endures, and the atmosphere thickens and transforms. Every process is interconnected. The collision set the tilt drives climate variation. The satellite stabilizes rotation. The rotation shapes atmospheric circulation. The atmosphere regulates temperature. Temperature controls geology. Geology feeds the atmosphere. Together, these systems evolve in tandem. Time stretches onward. Millions of years blend into tens of millions. The planet continues cooling, changing, cycling through extremes and recoveries. The environment remains hostile, but it is no longer purely destructive. It is becoming permissive. The threshold approaches slowly, imperceptibly. Conditions are aligning, shaped by forces set in motion long ago. Heat dissipates, pressure stabilizes, chemistry advances. The planet's surface stands on the brink of a transformation that will redefine its future, as the long aftermath of the collision continues uninterrupted, carrying the world forward toward the next irreversible change.